My name is Edith, and it's for the well logging class. We are the section D. So for today, our assignment was first to describe the gas effect and shell effect and its importance on well logging, and then to describe hydrogen index and the different value for oil, water, and gas, to read logs and to see how to identify different lithology while reading different logs, and from logs how to evaluate different values like peak size, salinity, different salinities, pressure, and temperature.
Hi, I'm Carver Stone, and today we're going to be talking about the log response from the Texas number 1 well from the depths of 8020 to 8060. This is from the Colorado School of Mines, Lab 4 for the well logging. This is question number 5. So at first, we're going to look at the 4 different types of logs and the log response from the depths of 8020 to 8060. We have a gamma ray plot, a resistivity plot, a density porosity and neutron porosity plot, and a photoelectric log on the right. So working from left to right, we're going to analyze what's going on in this formation. So first with the gamma ray plot right here, from 8020 to 8050 right here, we have low gamma ray, usually indicative of sandstone or limestone. And then at 8050 to 8060, we have higher gamma ray right here, which is usually indicative of a shale formation. On the resistivity plot over here, we have 2 different plots, a shallow and a deep resistivity. So from 8020 to roughly about 8040, we have high resistivity for both deep and shallow readings on here, indicating the presence of hydrocarbons. And from 8040 down to 8060, we have low resistivity, which indicates the presence of water in the formation, which generally has lower resistivity than hydrocarbons. Also, the difference between the deep and shallow readings on here, we have a higher deep reading, which is indicative of the hydrocarbons presence, versus the shallow reading, which shows the influence of mud filtrate into the formation, which has a lower resistivity than the actual hydrocarbons in the formation. The difference between the two would be the displaced or the movable oil index. Working on the density and neutron porosity plot over here, you can see at the very top right here that we have a crossover right up top right over here, that our density porosity crosses over our neutron porosity, which shows the influence of usually gas in the formation right here. So the difference between the two, usually from 8020 to 8030, this type of response would be indicative of gas. Right here would be your gas-oil contact. And as these things get narrower together, this will be the presence of oil. Your oil-water contact would be right here when the lines converge, going all the way down to 8050. At that point, your neutron porosity then crosses back over with your density porosity, which is indicative of the shale down here. And the photoelectric log over here, which measures the hydrogen index, confirms that we have the assumption that we are using a sandstone as our matrix. So the value of around 1.8 all the way down to 8050. And at that point, you can see it increase to about 3 to 4 during the shale response over here, also confirming the presence of shale in the formation. And this is what a typical well log response looks like, or interpreting a well log in a conventional formation.
My name is Seth Hansen. This is well log number 6. We are interpreting a log header to solve for the mud filter resistivity at 6 degrees Fahrenheit, which is 0.36 ohm times meter. We can also find our condensate water resistivity at 6 degrees Fahrenheit, which is 0.034 ohm times meters. We can also find our boil temperature, and that comes out to 147 degrees Fahrenheit. The reason why we do this first is so we can come back up here and use the Arch equation to solve for the mud filter resistivity at the reservoir temperature. And through this, we found that at higher temperatures, there's lower resistivity. We can also use that to calculate the condensate water resistivity, which is the same process as this first one, but in reverse, since we're given the resistivity at 60 and have to solve for the reservoir. And we can solve that through, and then finally, to calculate the borehole pressure, which is going to be our rho GH equation. We are given our mud density, which is 9.6. We can divide that by the density of water, and multiply that by our pressure gradient times our height, and then add on our conversion factor from PSIG to PSIA, and get our final borehole pressure.
So my name's Hayden. We're going to be talking about 1G on Lab 4 today, which has to do with the hydrogen index. The hydrogen index is based on the number of hydrogen atoms that you find in 1 unit cube of pure water. So obviously, pure water has a hydrogen index of 1 to 1. Duh. Oil has a hydrogen index of 0.9 to 1, typically. And gas is much lower with a ratio of 0.1 to 1. It has a much lower density. You can also use the hydrogen index to determine lithology within your reservoir. Sandstone typical values are around 1.8, and shales range from 3 to 4.
Hi, my name is Sarah. This is question 1I. It has to do with neutron tools used for density and porosity readings in the well bore. So neutron tools shoot neutrons into the formation which collide with protons and return to the tool. So you can either have a gas effect or a shale effect with these tools. With the gas effect, the neutron porosity is lower because when the neutrons go out, they don't encounter as many protons, so not as many neutrons come back, which has a lower reading, which will cause a crossover between your porosity and density curves. This is known as the gas effect. The shale effect encounters more protons, so more neutrons come back, which would raise the reading of your tools and would, in effect, mask the porosity reading of the other neutron tool, so the curves would come together, which is the shale effect.